projector off because it apparently takes 30 seconds to power off before I power it back on. That was not the problem. Anyways, sorry for the delay. So today we'll be looking at some recent applications. Nothing in this lecture is part of any subsequent homework or final exam, just to give you a little bit of survey into some of the things that people can use machine learning for and people have tried in recent years. Quick show of hands, how many people went to at least part of the AI for Science workshop last Thursday? Okay, great. So some of the stuff we'll be talking today, at least in terms of how we use machine learning, is very much thematically consistent with what you saw in the workshop. Of course, these applications are a bit different. And so we'll look at 4 applications today in edge detection, speech animation, embeddings of visual style, and very, very briefly generating faces. We'll probably talk about that in more detail in a future lecture. Let's start with edge detection. It's a fairly classic computer vision problem. The basic idea is the X, your input, is an image, perhaps 3 channels, perhaps black and white. And what we want to predict is the edge mask of this image. There's a little bit of ambiguity in how you define edge mask, but roughly it corresponds to what you see in the bottom row of images. That's the prediction. Okay? So what's the output space? Well, if the input space is, let's say, a 400 by 300 image, so that's 120,000 pixels, not counting the fact that you have 3 channels per pixel. Are we going to is that the output space? Are we predicting a Y that is 120,000 dimensional? If we make that discrete, binary, +1 or -1, or 0 or 1, a naive calculation is there's an clearly a huge number of labels, one that grows exponentially with the resolution of the image. And this naive mapping from input to output is probably not what we want to do. So the first half of the types of applications we'll be looking at in this lecture are on what's called learning reductions. The idea behind learning reductions is you take a complicated problem and you convert it into a simpler one, or a set of simpler ones, or a sequence of simpler ones. And these simpler problems are ones that we can use off-the-shelf machine learning approaches for, like decision trees and neural nets, for example, like Keras. And then we write a procedure, typically a fairly simple procedure, that recompose the predictions for these simpler problems back into a prediction for the original complicated problem. So in order to come up with such a reduction, we need to come up with some sort of assumptions about the structure of the problem. And so here are a few properties that we can sort of roughly state, at least at this level of informality. So this is a fairly informal statement, but here's how it goes. Local patterns matter. What does that mean? That means if I look at the description of how the edges should be at any portion of the image, like this head right here, by and large only depends on the local image area. So to determine whether or not there's an edge here, I don't need to look at, for example, the bottom left corner of the image. That's sort of the assumption, and we can make them more or less precise depending on sort of the level of rigor you want. And the other assumption is that within this local window, right? We want to within a local window of the image, the relationship between what is an edge and not an edge as a function of the neighborhood of pixels is a highly complex or nonlinear relationship. Those are the 2 assumptions that we'll be making. Okay. Right, so I just actually alluded to this in the previous slide. Weak global properties, which means that the edge detections are local. So if we want to predict the edges in this part of the image, it doesn't really require modeling what's going on over here. Of course, this is not 100% true. We could always create counterexamples where this is not true. But the assumption is that this is basically sufficient. Okay, so then we can do a decomposition where we're going to train a model to predict on patches of the image. So let's say, for example, 16 by 16. So we have this image classifier that takes a 16 by 16 patch of the image and classifies it into an edge mask. So a 16 by 16 0-1 mask. And we're going to slide it across the image and make predictions. So that's the basic idea. And if we trained a classifier, this classifier, then the recomposition, right? The decomposition is to decompose it into learning. A reduction or decomposition is to decompose it into learning only over 16 by 16. And the recomposition is, okay, after we train this 16 by 16 classifier, we'll slide it across the image and aggregate the predictions. That's the recomposition. So this is a fairly simple form of a reduction or decomposition, but I hope it starts to illustrate the idea. Okay, so we'll be using decision trees. You can use other things like neural nets as well. It doesn't really matter at this level, but we'll for the most part, we'll stick with decision trees in the first half of this lecture and move on to neural nets in the second half. Again, this is just a reminder of what decision tree is. And so, okay, one of the things that's different is that now each leaf node needs to predict a 16 by 16 edge matrix. Okay, that's kind of different. And it needs to do so in a way that's sort of somehow reliant on the training data that gets partitioned into that leaf node. So, you have oh yeah, I should mention, sorry, I forgot to mention that this is a supervised learning problem. So we have a training set that's a collection of XY pairs, where this is the X and this is the Y. So someone, possibly a poor PhD student, painstakingly annotated these images. Sorry, that was probably not a funny joke to some people in the audience. Okay. So we had the ground truth labels, then we can just predict the average 16 by 16 patch label, and have that be the prediction. So prediction is very fast. I'm not talking about training right now. Suppose we've trained the whole system. Prediction is super fast, right? You just slide across the image and average the results. And we'll talk about other forms of approaches that are not like this in future lectures. For example, for those of you, we'll be looking at approaches based on dynamic programming to make these types of predictions in future lectures. We're not talking about that today. Those algorithms are also called Viterbi algorithms for sequence models. But we don't need to do that for this. We just slide it across, and it's actually embarrassingly parallel at prediction time, right? So the only thing that, or one of the big things that we have to do now is reason about how to actually construct the decision tree training algorithm, because okay, it's over 16 by 16 patches of Y labels, edge masks, and we need to somehow come up with an appropriate notion of an information gain criterion. Also, what is the query set? Okay, so the way that the authors of this paper, Structured Random Forests for Fast Edge Detection, decided to go about this problem, and this was published at a top computer vision journal about 5 years ago, is as follows. By the way, Piotr Dollar was a postdoc here at Caltech. He is now at Google DeepMind. Suppose that this is the set of 16 by 16 labels that we have. Remember, when you compute the information gain, you only look at the labels. The query set conditions on the inputs, which is the image, and the information gain criteria is conditioned on the distribution of labels in your node, and whether or not that gets improved as you split it into two subpartitions. So suppose this was the set of edges, right? And just qualitatively, right? So these edges look kind of the same. They seem to be covering a similar type of, edge mask phenomenon, local edge mask phenomenon. And these edges seem to be, describing another local edge mask phenomenon. So if we have found a query on the images that split this leaf node, this internal node, into these two leaf nodes, we want some information gain that says this is a high information gain. On the other hand, if we had a query on the images, on the pixels that split it into these two leaf nodes, we want an information gain criteria to say that this is a low information gain. This is a bad split. That's the basic intuition. So there are a few ways that one could do this. And I don't mean to suggest that this way is the best way, but it is the way that, or this is a simplification of the approach taken by the authors in this paper. And I think it's kind of an interesting approach. And I think, so I'll just go over it at a high level. So what the authors do is they first map labels to a coordinate system. And so what does that mean? So they have this abstract coordinate system. You could think of that as an embedding, if you like. And for each coordinate in this coordinate system, we're going to choose a random pair of pixels. Let's say these 2 pixels. This is all relative to a local 16 by 16 patch, by the way. And we set the coordinate to 1 if these 2 pixels are in the same segment and 0 otherwise. So if coordinate 1 corresponds to these 2 pixels in a 16 by 16 patch, then for this image, we set that coordinate to 0 because they do not belong to the same patch. And these two pixels do belong to the same patch, so we set coordinate 2 to 1. And these coordinates are defined randomly. So for every training example, which is a 16 by 16 image plus a 16 by 16 image patch, we have this predefined set of coordinates, and we set them to 1 or 0 depending on whether or not these 2 pair of pixels belong to the same patch in this particular training example or not. Then we can cluster the training labels using this coordinate system, using k-means clustering or any of your favorite clustering algorithms, using this coordinate system. So now we've reduced the training labels to k clusters, and now we can treat this as multi-class classification. Your impurity measure is simply multi-class entropy, which is just a straightforward generalization of entropy that we saw in the decision tree lecture. So in this simple example, we have 2 clusters in this simple example, and if you do all pairs of pixels, you can probably come up with a very good coordinate system based on what pairwise coherence of pixels, whether they belong to the same patch or different patch. Of course, people don't do all pairs because it's quite expensive. But suppose you had enough coordinates so that you can sort of identify these 2 clusters, then the ideal split on the images of the pixels of the image, sorry, would split all one cluster in one leaf node, and all the other cluster in the other leaf node. And if we got a query on the images that did this split, that's a pretty good split. And that's the basic idea. Any questions at this point? Okay, so the other thing that one needs to address now is, okay, the query set. Remember that the query set needs to be defined on the input, the X, which in this case is a 16 by 16 patch of RGB values. And so I won't go into too much of the details. They're basically based on color gradients. So for example, do the image get darker as you go from left to right? Does the image get more blue as you go from left to right, etc., or top to bottom? These days, this was done in 2013 before deep learning really took off. And so these days, you might replace this with something more based on deep neural nets, but it doesn't really matter at this level of abstraction. It's a fairly domain-specific query set. And here's how we put it all together. So we have our original training set, which is which is a large image pixel pair, and then we chop it up into overlapping sets of 16 by 16 input-output examples. And that's our S hat. And now we train our decision tree on X hat using the recipe I just described. And after we have this decision tree, we predict by sliding the decision tree over the image. Note that nothing here prevents us of using a neural net instead of a decision tree. Some of the design decisions of how to reason about these XY pairs might be a little bit different with a neural net, but otherwise, this decomposition approach is somehow modular. Any questions? Okay. So here are some results. There's some post-processing involved that I won't go into, just to clean up the predictions a little bit. But So that's what these 4 versions of the approach indicate. There's different levels of post-processing you can do. But this is some of the results you get. So you get, this is the original image, this is the ground truth. It's a little bit pixelated because of the resolution. One of the things you notice about this prediction, because it makes multiple predictions at each pixel and averages them, is that the edge masks are a little bit fuzzier or blurrier than the ground truth. And that's a feature or a bug depending on your point of view. But you can see that these are some of the results. One of the nice advantages of this approach is that it is super fast at test time. Right? It is, in some sense, it's embarrassingly parallel. If you had 64 cores, you could just shard the image patches into 64 partitions and run the decision tree on all 64 and then recombine the results. And so that was really what this approach was going for at the time in 2013, was they wanted an approach that was as fast as possible. And so the accuracy measures compared to previous approaches are comparable. The speed at which one can make predictions is much faster. And the basic idea is that at 16 by 16, somehow you've captured enough of the local properties to make a reasonably accurate local prediction. And then if that's the right level, then we can train these models and then run them really fast at test time. For other images, maybe you need 32 by 32. For some smaller images, maybe you need 4 by 4. But you want your local window to be as large as possible, to be large enough to capture enough of the local properties for you to make an accurate prediction, and no larger. That's the basic idea. Yes.
What happens to adjacent local results?
So these are predicting the average, right? That's why they look blurrier than the ground truth. So the ground truth is, a human annotated, like very fine edge lines, and you see these are blurrier. And so that's a result of averaging. So if they disagree, you average the difference. That is either a feature or property, a feature or bug, depending on what your use case is. Like one could make the argument that these edge detections somehow are more useful in some applications, because if you're forced to make a single really fine-grained edge detection, do a really fine-grained edge detection, if you're a little bit off, it just looks weird, right? Whereas this, you can make a much more graceful, you could do much more graceful downstream reasoning because you have some notion of uncertainty. Okay, so we're going to take some of the themes from this idea and apply to a completely different approach in speech animation. And I'm going to have to do something kind of hacky here because I couldn't get the audio to work with the audio system. At least I don't think I did. Yeah, so I'm going to have to play the audio from my laptop, unfortunately. But the basic idea here is that if you want to automatically generate lip syncing of an animated character using only input audio, how do we do that? And this is something that's very time consuming for artists to do. And so this is a project that I worked on, and the approach that we developed was actually inspired by the previous paper. And so here is one audio, and I apologize, I have to play the audio from my laptop.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
So that's Barack Obama and our animated face lip syncing to him. So I'll just do it again.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
Okay. So here's the training data. It's about 200. So our actor, his name is Ken. He's quite famous in the computer graphics community now. We sat him in front of a green screen, and we made him say about 2,500 sentences. These are recorded at 30 hertz, so it's about 10 hours of recorded speech. It was pretty tired at the end of the day. And then we used standard computer graphics techniques to build a model of his face. It's called an active appearance model. There's about 30 degrees of freedom in this face. You could think of it as a virtual puppet, if you will. And so, this is the, what is this way? This is the word, this is the phonetic decomposition of the word X-ray film. And this is what his mouth looks like as he enunciates the words X-ray film. Again, the temporal resolution here is 30 hertz. So one frame is 1/30th of a second. So here's the prediction task. We have an input sequence, which is, in this case, a sequence of phonetics. So suppose we had the frame-by-frame phonetic decompositions of the audio. So this could be, for example, the International Phonetic Alphabet. Then we have an output sequence, which is a frame-by-frame decomposition of the parameterizations of Ken's face as he is saying this input sequence. So if our model of Ken's face is 30-dimensional, you can think of each y as living in a 30-dimensional space. And so here's just an example. So this is the frame-by-frame decomposition of the word prediction. And this is visualizing the first dimension of a 30-dimensional face model. And the first dimension corresponds to how wide open the mouth is. So if the value is a big negative number, Ken's mouth is completely closed. And if the value is a positive number, Ken's mouth is wide open. So as you start saying the word prediction, the mouth sharply opens, then stays open for a little bit, half closes, stays half closed for a bit, and then closes some more. And so that's what we want to predict. We want to be able to predict how basically these temporal sequences in response to phonetic inputs in a way that matches the ground truth. So again, we can make the same types of assumptions as in the previous application. In a local window, there's a highly complex relationship between the input phonetics and the output animation. This is also known as the co-articulation problem. So the way you pronounce the R sound or the is sound depends on the local context in terms of the way your mouth is shaped. On the other hand, there seems to be minimal long-range dependencies, right? The way your mouth is shaped to pronounce the end of the word prediction is roughly the same no matter if it's prediction or construction or election. Doesn't seem to matter too much. This, of course, is an approximation, but it seems to be a pretty good one in practice. And to illustrate what co-articulation means, let me just show you an example. So this is Ken voicing the phone K within different words, and you see the huge range of mouth shapes. Okay, so what does that mean? That means, in the past, when people did animation for animated characters, they would have like a prototype mouth shape for every phone, for every syllable, and then just stitch them together using cubic interpolation or something. And that didn't really look great. And this is actually the problem why. Right? The local relationship you need to capture for these for lip syncing is much more complicated than just a single shape per phone. So we want to really nail that. We want a predictor that, given a good local window, can really accurately reconstruct the local curvature of the mouth shapes. But of course, we can exploit the fact that there are weak global properties, just like in edge detection. We don't need to model the whole sequence in its entirety. So we can, again, decompose into a moving sliding window approach. Okay? So we have prediction as the input. We chop it up into overlapping sliding windows. So here it's length 5, just for illustration. We send each of these through a predictor that predicts a length 5 output of the parameterizations of Ken's lower face. Recall that each parameterization of Ken's lower face is 30-dimensional, so this is a 150 variable regression problem. Pretty hard, but well within the capabilities of modern machine learning. So this is just literally 150-dimensional regression, as opposed to one-dimensional regression. So nothing really changes. You can, if you don't want to use decision trees, you can use neural nets, and you just call Keras, and the output is 150-dimensional regression. So there's 150 output nodes. You minimize squared loss. And then we recompose by averaging everything together, and that's the output. And again, things are very fast here. So the only thing that requires machine learning now is this 150 variable regression problem. And that's something that you can actually implement off the shelf. So it's a little bit of Python script to do this, a little bit of Python script to do this, and then Keras to do that, and you're done. OK, so how do we do training? The original training data had variable length trajectories. We want to only look at fixed length trajectories around a small local window, so we chop it up into input-output pairs of the following form. Again, I'm only visualizing one dimension of a 30-dimensional face model. Keep in mind we're only visualizing one dimension here. And then we train. We use standard training on this modified training set data. So we've actually nowadays have done this for both decision trees and neural nets. For neural nets, the predictions are actually a bit better. But I think the decision tree model is somehow more interesting to linguists and people who study speech. So this is actually the top of the decision tree that we trained on this data set, on the top 3 layers. The input length is 11, so 11 frames is about 1/3 of a second. And frame 6 is the center frame. So for any input speech fragment of 11 frames long, 1/3 of a second long, this is the first question the decision tree asks: is frame 8 a vowel that contains an a, like a, ah, etc. I don't know what that means. Someone who studies speech might be like, okay, it's after the center frame, which is frame 6. Maybe there's like some notion of anticipation of what you're going to say next could influence the shape of your mouth at the center frame. It's my interpretation. I don't know if it's true or not. It seems reasonable to me as a first-order approximation. If anyone here studies speech, please don't call me an idiot, although I probably am for saying that. But that's the basic idea. We could actually use this as a tool to understand how humans enunciate speech. I have the full decision tree, by the way, somewhere. It's got about 5,000 leaf nodes, but that is actually small enough that you can actually exhaustively study if you're really, really, really into this stuff. Oh yeah, this. So sibilant, I believe means. Okay, I'm being recorded, but I believe sibilant means the tongue. Post-alveolar means the tongue touches the roof of the mouth as you speak that consonant. So it gets pretty complicated. And we took this query set. We took this query set from people who study speech. So they gave us a set of queries, and we basically enumerated all the possible set of queries over all possible frames in this 11-frame input snippet. Okay, and then the regression is just, for decision training, is pretty easy. It's just 150 variable regression, so it's multivariate squared loss. So that's the splitting criteria. Any questions at this point? Okay, so here's another result. Just apologize again for the audio coming from my laptop.
Tonight, I've returned from a trip to the Gulf Coast to speak with you about the battle we're waging against an oil spill that is assaulting our shores and our citizens.
Let's play that again.
Tonight, I've returned from a trip to the Gulf Coast to speak with you about the battle we're waging against an oil spill that is assaulting our shores and our citizens.
Okay, so here's what some of the predictions look like. So this is the input learning. And so this is the frame-by-frame decomposition of learning. And then this is, again, dimension 1, which is how wide open the mouth is as you say the word learning. Here is SIGGRAPH. So there's a lot more consonants and things going on, so the mouth opens and closes a little bit more. SIGGRAPH, if you don't know, is the top computer graphics conference. We can do side-by-side user studies, so based on our approach and some other approach.
Where only one club existed before, he says, two will flourish henceforth.
I'll play that again.
Where only one club existed before, he says, two will flourish henceforth.
So how many think the left one looks better? How many think the right one looks better? Really? I'll play it again.
Where only one club existed before, he says, two will flourish henceforth.
Huh. Well, I mean, the left one was ours. And we did a user study like this. It's it's controlled, and we show that our approach, on average, is more preferred compared to animations generated by baselines. So let me talk a little bit about the whole pipeline. This was motivated by a collaboration with the Walt Disney Company. So you start with the input audio. You do off-the-shelf speech recognition. So your phone can do this while it pings the cloud. You take that speech recognition, you feed it into our approach, and then you do off-the-shelf computer graphics techniques called retargeting to retarget from our model of Ken's mouth to any animated character. And then you can import this animation into an editing software such as Maya, where an artist can add low-frequency animations, such as smiling, on top of our high-frequency animations for the lips. So retargeting basically means that you have a reference face, and you want to map animations from the reference face to a target face. This is very much like having an intermediate representation or an intermediate language by which you develop your approach, and then having then retarget or specialize to application-specific stuff. Yeah, so I won't go into the details here, but this is, so you're aware, this is quite an involved collaboration that spans multiple research disciplines. And you get results that look like this.
Do I look funny to you? I may be a chimp, but I'm dressed better than you.
I'm a PhD specializing in computer graphics and facial animation. But at night, I'm a level 10 operative for a secret organization.
But we are now on different frequencies.
My speech is pretty good, don't you think? Meu português é ainda melhor, não acha?
So because this approach operates at the phonetic level, it's actually to a fairly large extent language agnostic. So here's some more examples.
Deutsche Wörter sind sehr viel länger als englische Wörter. Mal sehen, ob das trotzdem funktioniert.
한 가지 언어는 충분하지 못해.
Jeśli kiedykolwiek będziesz odwiedzał Polskę, polecam Kraków.
මම දල්දා මාලිගාව වන්දීමට සෙනසුරාදා හවස ගේමි.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
So it would have taken an artist to animate at that level of temporal frequency, probably days to animate those short snippets, and we can do this basically in real time. Singing.
Somewhere over the rainbow, way up high, and the dreams that you've dreamed of once in a lullaby.
Oh, Danny boy, the pipes are calling from glen to glen and down the mountainside.
So the quality of the animation obviously depends on the quality of the target. So the chimp rig was very well designed. Some of the other rigs were lower quality. And so, of course, some of the results are influenced by the quality of the target rig. So just to recap, any questions, by the way? Yes?
I don't know how practical this is, but I could imagine in some speech, if you're just taking an input audio where it's not completely, I guess, continuous, like maybe people have like idiosyncratic like mouth positions between their words. Is that ever something that comes into play here?
Yeah, that'll be a problem for here. The training distribution has a certain distribution of pauses between words. And if what you're going to input to it is really different from that training distribution, the model might get a little confused.
Right.
Of course, the default answer is to add more training data. That has also its own issues, but that would be one issue, one way to address that. Yes?
How does enunciation affect the training? Like you can't have really poor enunciation, for instance, if you have a hard.
Right. So the retarget. Great question. So the let me just, can I go to it? And PowerPoint crashed. All right. Glad you guys got to see that. Your question was, how does CANs? Let me just pull up this slide. And I opened it twice. You gotta love Microsoft on a Apple. Okay, let me just pull this slide. Okay, so the question was, how does enunciation affect things? So I think this is an interesting question. So there's always this question in machine learning for various applications. Should we train on really clean data, or should we train on noisy data? This is another way of phrasing your question. And we chose to train, sorry, I think I'm developing a slight dyslexia. We chose to train on completely clean data. And there are certainly many domains where that's the wrong thing to do. The reason we chose to do that is because, let's see here. The reason we chose to do that is because in this pipeline, we assumed that this step works really well. Google probably spent about $10 billion on their speech recognition or something, or a ridiculous number. I don't actually know how much that number is. I wouldn't be surprised if they spent something on the order of billions of dollars on their speech recognition. It's something that's very important to them across all of their products. So I wouldn't be surprised. So we're basically saying, okay, if that part is clean, then we're good. If we wanted to train this model that is invariant to all the variabilities of human speech, and not work rather than working at the phonetic post-recognition phonetic level, then we would need a much larger training set than 10 hours of spoken speech. And so there's a trade-off there. It's part of the whole process of understanding where machine learning can make the biggest difference, right? Machine learning was already used. A huge training set was used to train this guy, right? Artists have developed these guys, right? So the animation artists at Disney have developed these guys. What's missing is simply a mapping from phonetics to animation. And so if you can isolate the part that you want to use machine learning for, you can do it with a fairly modest amount of training data. Now, if you want a general purpose thing, like for example, if we're doing self-driving cars, it needs to work in the wild, wild west, or what, that's a different story. So it really depends on the use case.
I guess that question stems from, you said this is fairly language agnostic, but how does it handle dialects or accents as well?
Right, so that's a great question. So as long as you have the phonetic decomposition, we're going to animate in a way that looks like Ken.
Gotcha.
Okay? And with retargeting, you can capture systematic biases. So if this character tends to open mouths wider, we'll just take that eigenvector and make that eigenvector wider, right? It won't handle dynamic biases where that only occurs sometimes. But any kind of systematic bias, like maybe I have like slurred speech and my left side of my mouth opens wider, any kind of systematic bias, this type of retargeting approach can handle.
I see.
So
you can apply biases both.
That's what retargeting is, right? These are different mouths, right? Yeah. So if you want to do dynamic biases, I think that's an unsolved problem at this point in terms of this type of systematic solution. Yes?
Is there a way you can run this backward for lip reading?
So if you've ever seen, I think they have a YouTube channel, it's called Bad Lip Reading. I don't know if you guys ever seen that. So lip reading is quite hard because it requires understanding of language. We don't actually need any understanding of language here. We've actually offloaded all understanding of language to speech recognition. The degree to which we need to understand language has been offloaded to speech recognition. If you want to do lip reading, if you've seen bad lip reading, they take like scenes, famous scenes from movies or whatever, and they come up with a sequence of audio that matches those lip movements, and it's typically done in a humorous way. That means that there is a one-to-many mapping from the audio that you observe, or the lip movements that you observe, to plausible sounds that could have made those led to those lip movements. Which means you need to know context, you need to know language, you need to know coherence of creating constructive sentences, you need to know all of that in order to do lip reading. We've done it. I have it. My collaborators have. It's complete gibberish, but it's consistent with the mouth shapes. So in order to do it in a more intelligent way, we'd have to have a much bigger model that really understands language at a more sophisticated level. Whereas if you just take phonetics and map it to lip shapes, that's a fairly one-to-one deterministic mapping for the most part, at least to a first-order approximation. Okay, so moving on. So let me just recap learning reductions. So we know how to solve standard machine learning problems. That's what this class is all about, at least the first half of this class. We have the tools. You implemented some of these yourself, but for the most part, after this class, you'll be just using toolkits like scikit-learn, XGBoost, so on and so forth. And the idea is that we want to reduce complex prediction problems to simple ones. So for example, multivariable length trajectories to simple fixed length multivariable regression. This is of course still not difficult, but it allows us to reuse tools that we've built in the past in a way that is easy to engineer, easy to maintain, easy to debug, and easy to reason about. And this is similar to other reduction problems. So for example, when we do something like when we study complexity theory and we look at NP-complete reductions, right? We really only have one NP-completeness proof for a 3-sat, I think, if to the best of my understanding. Every other NP-complete proof is a reduction to 3-sat, or by transitivity, a reduction to 3-sat. Of course, so by analogy, like if we just know how to figure out how to reduce some complicated problem to classification, maybe a set of classification problems with widgets of classifiers or whatever, but we know that we have a really good classification module called TensorFlow, then we just write some Python wrappers and everything just works with minimal engineering and debugging overhead. And what's interesting to me is that some of these reductions have provable guarantees. So if I can prove that these reduced learning problems have nice properties, I can prove that the recomposition. So if the reduction is property preserving, then whatever properties you can prove about the reduced problem lift through the recomposition. How that works in NP-complete reductions is your reduction has to be polynomial time. Your reduction has to be correct, and it has to be polynomial time. That's what it means to do an NP-complete reduction. Learning reductions have different requirements, but that's the general flavor. This is an area of research that I spent a lot of time on myself. So if you're interested, we can sort of talk, during office hours or whenever, if you're interested in learning more about that. So there's a set of other reductions that people have in the past have studied. Here's a link to some nice set of earlier work on learning reductions, if you're interested. So I'm running a little short on time, so I'm going to speed through the next couple of sections. Learning visual style. So the motivating application here is, can we find sets of clothing, in this case, based on their visual compatibility? So this is based on this paper, which appeared at ICCV, which again, one of the top computer vision conferences about 3 years ago. And so, just by just by example, you don't want if you're going to wear formal wear like a suit, you probably don't want to wear a pink polka dot sock or whatever that is. And so can we infer these things from the data? So the training data is scraped from Amazon. You have a ground set of elements, items, about 1 million. Each item contains an image and a category. So for example, the categories could be coat, belt, pants, socks, etc., things that are related to clothing. And then we also can mine these pairwise relationships, such as frequently bought together. Okay? So if two items, like a coat and a belt, are frequently bought together, we're just going to interpret that roughly as being visually compatible, at least for the purposes of this project I'll be describing that these people did. Okay, so what's the training objective? We want to learn, so theta are all the parameters of the model, neural net, weights, and anything else that you might want to learn. This is a minimization problem over all of them. We want to learn an embedding of an image. So each X is an image, such that they belong to two pairs, compatible pairs. So L plus penalizes if the location of these two embeddings are too far from each other. And this is the second sum is over incompatible pairs, and L minus is a high penalty if the embeddings of these two images are too close to each other. That's the high level idea. And we're also going to only do pairs in different categories. So, if you buy two coats, people frequently buy these two coats together, it's not that interesting in terms of visual compatibility, because these authors are interested in visual compatibility from the perspective of matching up different types of clothing. Okay. So we're gonna use neural nets to learn this embedding. So this is a convolutional neural net, which we covered a while back. You get an image. This is one of the famous, this is the AlexNet, one of the famous neural nets from about 5 or 6 years ago. And we go through a bunch of convolutional filters, and we get this fully connected layer. And then what they did for ImageNet was they mapped from this fully connected layer into 1,000 class logistic regression for ImageNet. That's what they did. We're just going to throw away. We're going to take the same let's say we take the same architecture, although you can use any convolutional neural net architecture you want. But let's say we took this architecture, and instead of doing multi-class logistic regression at the very end, we're just going to use this last hidden layer. So this is this particular hidden layer is 4096. So so now we have a 4096 dimensional embedding from an image. That's the basic idea. So one of the approaches that was used for this is not the only approach, but this is one, is called a Siamese convolutional neural net. So you have a pair of images. I know that the names are a little, they can get quite exotic or crazy, depending on your perspective. So we feed that through a CNN, and we get this embedding. So this is the last hidden layer of these two convolutional neural nets. And then we apply a loss function on this pair, whether they should be closer to each other or further apart from each other. That's and then you do back propagation, chain rule through that to learn the parameters of this neural net. And the reason why it's called Siamese is because these two neural nets are the exact same model, right? They're joined at the hip or whatever. So that's the idea. We have a single neural net that has predicted the embedding of a pair of images, and then we want that pair of embeddings to be either closer to each other or further apart. And we have lots of pairs of images of compatible and incompatible, and then we do stochastic gradient descent on this objective. And this is implementable in for example TensorFlow. Yes.
So would you get the embedding before then applying this training goal, or is it all?
This is the training goal.
Okay.
So when we did the deep learning, the only signal you get from the weights of the neural net is from, let's say, multi-class classification. Here, the only learning signal you get is from this loss function. I'm ignoring regularization, by the way. I'm not showing regularization in this objective just for brevity. You also have to regularize the weights. Okay, I mean, there's some details that that the authors had to deal with. First of all, you want a smaller embedding. 4096 is too large, so they typically use something smaller than 4096 for the final layer. And for the negative pairs, it's actually kind of interesting, right? We don't have explicit negative pairs. People on Amazon don't tell you these two pieces of clothing do not fit to each other. They simply have a lack of positive influence, right? There's simply lack of a positive signal, not an explicit negative signal. And this arises in a lot of training data that you would use that's extracted from human behavior. For example, if you engage on social media like Facebook, most of the time there's only positive feedback and not negative feedback. I mean, in terms of just liking or not liking a post, not in terms of the textual content. And this is true for the most part. Like in Amazon, right? The positive feedback is, okay, this person chose to purchase these two pairs of clothing simultaneously. If they choose not to purchase it, the reasoning for that is unclear. And so the way people deal with this is they just have an assumption about the base distribution of negative feedback. If you assume that all pairs that don't exist as a positive pair is negative, that's too strong of an assumption, right? There could be many reasons why they didn't choose to purchase these two pairs of clothing together. And so the one thing you can do is simply subsample the set of all possible negative pairs. Then this is the simplest thing you can do, and it's also the most common thing that people do in these types of domains. And so you get results that look like this. So this is a visualization of the embedding. And you see that you get these kind of you get pants, you get watches, you get things that I'm not sure how to describe this cluster, but this part of the embedding. You get jewelry, stuff like that, and you get hats and T-shirts that look like they match together in this part of the embedding, and so on and so forth. Any questions so far? Okay, so another task that they thought this embedding could be useful for, again, they've learned an embedding, so you can use the embedding for other applications. That's one of the things that people do with unsupervised learning or representation learning. And so, if this is the outfit you're thinking about buying, can you suggest the rest of the outfit? Can you do outfit completion by using this embedding? And so this is what's the prediction of this model. Some of them are better than others, but that's the idea. And again, this is based now only on the image, right? So we take all the possible images, we project it onto this 128-dimensional embedding, and then we also have the category of the item, and then we can do tasks like this. And the embedding was learned on, basically this embedding was trained based on user purchasing behavior on Amazon. So more formally, what they did was they had a query item, and this query item has an embedding and a category. And then for all the other categories, recommend the item with an embedding closest to the query embedding. That's basically what they did. Yes?
Is there anything weird or tricky you have to do to get to know lower garment? There's one where like a dress and it just so cool if you have to do something.
This one? That was probably hand encoded. Yeah, like the dress is both upper and lower. It was probably encoded. Yeah, I mean, there's going to be quite a number of corner cases. Some of them you can solve systematically. Some of them you just have to solve as a corner case directly. Well, okay, if it's a corner case, by definition, you cannot solve it systematically, unless you figure out a way to not make it a corner. Unless you figure out a way to frame it so that it's not a corner case. So this is the basic idea. We're going to take an embedding of the query image and a given category and recommend items from other categories with embeddings closest to the query embedding. Seems pretty straightforward. The problem with this approach is it's not robust to label noise. So this whole approach is reliant, at least as currently formulated, is reliant on the category labels being quote unquote good. So these guys. Now, it should come as no surprise that there is a non-trivial fraction of items that are miscategorized on Amazon, and this would be true for a broad range of e-commerce and online services. So some pants get misclassified as shoes, okay? No matter how you slice it, right, the embeddings of these two guys are going to be similar no matter how you create that loss objective, just because they're visually very similar. So what does that mean? That means that if this is my query, this will be the shoe that I recommend. So this is something we have to deal with for this particular application. Okay, so how do we deal with this? First, you have to make some assumptions. The first assumption, I think the only assumption we need to make really, is that miscategorizations are rare. They're the minority case, right? So even on Amazon, you might see a lot of them because Amazon is huge. Maybe only like less than 1% are miscategorized. So what that basically suggests is that we should, instead of predicting the closest shoe, we should predict the closest cluster of shoes. As a pre-processing step, we're going to cluster every category and then give it an input query category, let's say for pants. So we have an input image and we know it's pants. We find the closest cluster center of category shoes. So we ignore choosing items that are really close in terms of embedding space but are outliers compared to other shoes. And this works if miscategorizations are rare and there's concentration in terms of visual similarity of what shoes look like. Any questions? So there are other things that we can do with this type of representation learning. We can use it to do scores of things like who is the most coordinated or least coordinated. So, someone decides to wear. Let's see. Let's choose this guy. Right, and these are the items that he chose to wear. We can sort of look at, the distance of the embeddings of the items that he chose to wear, and that if that distance is small, then we say he's coordinated or his outfit is coordinated, versus someone else who, wears something where the distances are further apart, and we say that person is less coordinated or I don't know, more hipster. I guess it's up to your interpretation. Although, funnily enough, because this is based on purchase data, right? If hipster things become popular, the data will reflect that, and what is considered less coordinated may become more coordinated over time. And so you could actually build these embeddings that are time sensitive based on year or whatever, or context sensitive in some way. And so this is just a visualization of things that become more or less popular over time within this embedding. And you could see that different styles come in and out of fashion. Okay, very briefly, the last topic I want to talk on is on generating faces, also known as deep fake. This is YouTube. This is a video I scraped from YouTube. You can find the link of the full video down here and the paper here. This is the progressive GAN paper that was published about 1.5 years ago by researchers at NVIDIA. They are training reconstructions of faces based on a celebrity face data set. So now we're going to interpolate within this latent space. It's a little creepy, huh? Okay, so I'm not going to go into the details because it requires explaining a lot of things about probabilistic modeling that is beyond the scope of this particular lecture. We will have a lecture on deep generative models or deep probabilistic models later in this course, and that will cover the basics of how these types of models are trained. But the basic idea that I want you to take away from this approach in the context of everything we've talked about so far is that we have this latent set of latent variables, and there's a neural net that is a nonlinear mapping from the set of latent variables to an image. In this case, images of celebrity faces. This was trained on celebrity faces. And what that last video showed you was that as we sort of interpolated in this latent variable space, the Z space, we get different images. That's what you saw. And so if we were to think back and draw an analogy to eigenfaces, of course the analogy is going to be kind of superficial because we're doing nonlinear projections here instead of linear projections. But if we were to, and things are probabilistic as well, so the analogy is going to be kind of superficial. But at a high level, we can think of this neural net as like the U matrix in the SVD, and then this Z as the V matrix. So every individual Z corresponds to the coefficients of a person, and then that coefficients in SVD, it's because it's linear. It's basically corresponds to a linear combination of the basis faces to form the image. But in neural net, of course, for neural nets, this whole thing is nonlinear. So this operator is not a linear operator; it's a nonlinear operator. But there's at least at a superficial level, there's an analogy here. In the video you saw is simply dragging around that Z space. We could do the same thing with eigenfaces by dragging things around the V space. Again, we'll discuss this in much more detail in Deep Generative Models lecture. Any questions about anything we've talked about in this class? Okay, so the next few lectures will be focusing on probabilistic modeling. So some of the ideas that I glossed over will become, we'll talk